of the solutions. We talked about solutes, we talked about solvents, we talked about an idea of being soluble and insoluble, we talked about miscible, immiscible, saturated, unsaturated. We talked about all those different things. You should have these. I gave you these notes. I sent them over to you. A kid should have brought them to you the other day in Spanish class. In Spanish class?
No, I'm sorry, I didn't. I could ask my Spanish teacher, but
I had him run them over for you.
Thank you.
BDG has
I'll ask
there.
her for it.
That's where they came from.
Okay, thank you.
So I tried to get it to you.
No, I appreciate you trying. Sometimes stuff just gets lost.
All right, you've got it. You ready? Okay. All right. Well, let's do a real quick recap then, I guess, since some of y'all didn't see some of this yesterday. All right, so we had mixtures yesterday. We talked about suspensions like orange juice with pulp in it. We talked about colloids like fog. We talked about the Tyndall effect, where it reflects the light within that due to this Brownian movement, where the light part or light rays will bounce off of these particles that are moving around. Then we talked about solutions, and we had different components to that. We've got the solute and the solvent. The solute is dissolved in the solvent. So for salt water, which would be a solution, the solute would be the salt and the solvent would be the water. Okay. Then gave some examples of that. We talked about solubility. If something's able to dissolve in a solvent, it's soluble. And if it's not, then it's insoluble. And then we talked about the terms miscible and immiscible. And these pertain to two liquids. So if two liquids don't mix together, like oil and water, that would be immiscible. And if two liquids do mix together, then that would be miscible. Then we talked about how the water molecules can surround these ions and pull them off of an ionic compound, and the negative end of the water molecule would surround the positive ion, and the positive end of the water molecule would surround the negative ion. And then we talked about saturated. So saturated, you wouldn't have enough water molecules to surround all of these particles. And unsaturated, you would still have water molecules left over, and all of these would be surrounded. And then there's a special supersaturated, which I'm going to try to get a demo going for you for next week to show you that. And that led us to today's lecture, which is on solution concentration and kind of solution math. So solution concentration can be measured in a variety of different ways. If we're looking in terms of AP Chem, molarity is our most important one. So number 3 here is the most important one. If you don't understand how to do like some of these, that's fine, but molarity you got to have. And you got to have it for our next chapter, which is on acids and bases. Okay. Do you have anything to fill in for this?
Yeah.
Okay. So percent by mass and percent by volume are just part over the whole. Molarity, again, that's going to be important. Molality is going to be, and then mole fraction, every once in a while you run into that in AP Chem as well. Good? Yep. Ready to go? Okay. So here are, and I think these are on your sheet, these different formulas. Okay. Percent by mass is mass of solute over mass of the solution. If you think about that, this would be our whole, this would be our part. Volume, same way. Molarity is moles of solute divided by liters of solution. Now this one is where we get a little icky, okay? Because notice here, it's not salt solution down here, okay? It's solvent. So moles of solute divided by kilograms of solvent. All right, percent by mass. If we do this one, again, it's the mass divided by of the solution divided by the mass of solute divided by mass of solution. So part over whole, and then you multiply it by 100. So here's a percent mass problem. Okay, we have water here. It's got 3.6 grams of NaCl and 100 grams of water. So what would I do for this guy? Pray that my pen will work. That's what I'm going to do first. So here is my solute, right? Salt is my solute, so that's going to go on top. What's going to go down on the bottom? Well, this is your water. What is the formula for this? It's solution, right? On the bottom. So the solution is the whole. So this is just part of that whole. So what do I have to do to get the bottom value here?
103.6?
Yep.
Really?
Yeah. And then times 100. So 3.4, 3.5%. Easy enough? So do you see this is our solvent here. Or I'm sorry, this is our solvent here. And this was our solute. So that's our amount, solute. But to get the solution, we have to add them together. All right, good. All right, percent by volume is done the same way, except we're just using milliliters or liters here. You just need to make sure that they're both in the same unit. All right, so we've got a 100 ml bottle of rubbing alcohol. It's 70% by volume. What's the volume of the water in this solution? So if we have, so this is going to be 70 over here, but we want to take that out of percent form. So if we take it out of percent form, what is that?
Wait, how would you take it?
So to take something out of percent form, you just divide by 100. Because to get it into percent form, you multiply by 100.
Oh, okay. That's just like me nothing.
Okay, and then we've got 100 milliliters on the bottom. So this is going to tell us the amount of water on top here. No, that's going to tell us the amount of alcohol. Okay. So how many milliliters would my alcohol be? Huh? 70 milliliters, good. And if that's 70 milliliters, how much would be the water? Yep. Make sense?
Right, so there's 70 milliliters of alcohol and then 30.
Because 70 and 30 is 100.
Okay.
All right, so that brings us to molarity. And this one is the most important one of all of the ones that we're going to talk about today, because this one will carry us through into acids and base chemistry, which is our next and probably final unit of the year. And then it will also carry you in, and we use this a ton in AP Chem. So if you're coming on board with me next year, then this is really important. Okay. Yeah, I know. But if you go on and take college chem at all,
still need to know it.
oh yeah, this is huge. Like, yeah, you will use this a lot.
Oh, it still applies to you when you say AP Chem. We just talked about college and when it comes to
Yeah, and I do have college kids that will email me and ask me questions sometimes, or ask me, can you send me, like, a lot of times they want those orange sheets that I've given you and they've thrown them away. I'll have them like email me and ask me for copies of those things too. So yeah, so feel free to do that. I mean, I'm just hanging around here anyway, so you know, it doesn't take but a minute to attach it to an email and send it back to you. So
I'll just remember not to throw mine away.
So moles of solute, yeah, but sometimes you leave them at home and now you're in college and you're 2 hours away, and so it's not feasible.
You don't
So
even call your parents
they wouldn't be able to figure out what you want out of all those papers you got hidden in your room.
I know.
All right, so molarity is moles of solute. So you've got to get this into moles. So if they give you grams, you've got to convert it into moles. So this has to be moles. And that's going to be over liters of solution. This bottom thing has to be in liters, and commonly it's reported back in milliliters. So you got to be comfortable converting between milliliters and liters, and that's just sliding the decimal. So if you are given like 100 milliliters, that's going to equal 0.1 liters. So keep that in mind. Like, you've got to get comfortable sliding between these two units. And it's just sliding the decimal.
So sliding it.
Yeah, it's three spots. Mm-hmm. Yep. So go this way. And the reason why it's commonly reported in milliliters is because most of our equipment is in milliliters. And so that's why you have to get used to, but when you want to do your calculations, you've got to get it into liters. Okay? All right. So here we've got IV solution. We've got 100.5 mils of IV solution. It's got 15.1 grams of glucose. Okay? They want to know the molarity. So we've got to convert this grams of glucose into moles. So get that into moles and then divide it by liters of this solution. So see if you can get that done. So moles over liters. It's going to give you your molarity. Nope, 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 nope. Hold on. Let's try reading that again. 5.8 over 0.1005. .56. And this is a capital M for molarity. You will also sometimes see it written in square brackets with no unit. That still means molarity.
I got 3.
What did you get for this top value for your moles?
Got 0.028.
Okay, so you should have had 5.1
Well, how do you get?
divided by 180.
Oh,
Oh, wait a minute. No, I got it wrong. Did you guys get this? Did you get my answer? You didn't get my answer, did you? Okay. What is my
That's
problem?
what I have.
What is my problem today?
Wait, for the top one.
Yeah.
I divided them wrong too. So
Okay.
I don't think
So you and I are both having issues today. They're okay. We're having issues. They need to speak up and tell me I goofed something. Divided by 0.1005. All right, how about 0.282? Okay.
I'm pretty sure that's what I'm going to get. Can you just give me 1 second to finish?
Yep.
Thank you.
I'm going to go over here and just kind of lick my wounds.
No, you're good. I messed it up too, and I was trying to do it.
I know, but I'm the teacher. I shouldn't be messing it up.
Well,
and it's not even a Monday, y'all.
Well, it's a Friday. You're tired by Friday.
I am.
For us, it's only Wednesday. So I got 2.56 now. I don't know what I'm doing. I did 0.1105. Or sorry, 0.0283 divided by 11 or 0.1105.
Yeah, it's 0.1005 though.
0.283 divided by 0.1. We try.
No, it's not 0.11. It's 0.1005.
Oh my gosh, I can't. I'm seriously done. I'm so awful.
Are you good now?
And now I got 2.81.
Okay.
I'm so sorry. Oh, that is right, because you rounded it. Okay, I'm good now.
I gotta go back and get a piece of equipment. And then I can...
I'm so sorry.
It's okay, honey. Don't worry about it. Do I have one? No, I don't have one.
Sorry, guys. I'm always sorry. Love you, class.
I always forget to bring these things out for each lecture, and then I have to run back there every year and grab these things to show you guys. All right, so what we have is, this is a volumetric flask, okay? And it ends up having these lines on it where they're etched lines, and that gives you a volume reading for whatever's specified on the flask, okay? And this flask is designed to make 250 milliliters of solution. That's the only volume that this flask can measure, is 250 milliliters of solution. That's it, okay? This one's designed to make a liter of solution. It has one etched line, and that's all it's good for, okay? When we get in our solutions, okay, or when we get in our stuff in the bag, okay, most of the time it comes in a powdered form, okay? And we have to take this and dilute it down to whatever concentration we want. So I'm going to show you how to do those calculations today. So let's say that this is our sucrose, and we wanted to make a liter of 1.5 molar sucrose. I would need to measure out 1.5 moles of sucrose, and then put that in here, and then fill this up to with water until it reaches that etched line. And you've probably seen me throughout the year, like making some of these things up for AP and different things using this type of equipment. Okay, so we can't just add a liter of water in here and then dump the sucrose in, because then we would have a greater volume. It would increase the volume, and that doesn't work. So we have to add the sucrose in and then add in the water to make up the difference. So you measure the mass of the sucrose. You guys are going to have to do this in lab next week with copper sulfate. You measure out the mass of the solute, which you've calculated. You're going to put that into the volumetric flask. Then you're going to add the water until it comes up to that calibration mark. Make sure that you look for the meniscus, the bottom of the meniscus that should hit that calibration mark. Okay? And then you've got your correct amount. So, but what if we don't need an entire liter? Maybe I don't need a whole liter of this. Maybe I only need 250 mils of it. So then what we would have to do is we would have to convert the molarity that we want. So if we want 1.5 molar, and now instead of a liter of solution, I only want 250 milliliters, which is that liters, that would tell me how many moles I've got to make of this. And then I just convert those moles into grams. That makes sense? You're going to have to do this. So make sure you know how to do this. You have to do this in lab. So 0.25 times 0.15. Let's see if my fingers will work on this guy. So that would be 0.0375 moles of glucose. And if I multiply that by 180, that's going to give me my grams of glucose that I'm going to need. So 6.75 grams. So I'd add 6.75 grams of glucose into here. And then I'd add water until the bottom of the meniscus reaches this etched line. We also get certain things in, and you're going to have to do this as well as part. Yeah, go back.
Go back for just like 30 seconds. Sorry.
Oh, progress reports are due again.
Yeah, I'm good. Thank you.
Okay, we also get in certain things, and you're going to have to do this as part of your lab too. So you're going to initially make up a sample of this, okay? And then once you have that made up, you're going to make up another solution by diluting that stuff down. So you're going to have to do 2 different solutions that you're going to end up making as part of your lab. So certain things we get in, like our acid, for example. Acid is typically sent to us in high concentration. So hydrochloric is 12, what we call 12 molar. Oh, when we have this dilution, when we talk about these concentrations, the big M stands for molar. Okay, and we're talking about molarity then. So our acids, our hydrochloric will come in at 12 molar. Our sulfuric is like 18. Our phosphoric is like 13 or 14. They're really concentrated stuff. And it benefits us to get it in that way, because then I can take 12 molar and I can make anything less concentrated from that. And so I can get whatever range I want, but I can't take one of those lower molarities and make them more concentrated and know precisely what I've got. The other benefit is it's much cheaper to send me one container of this concentrated stuff than a bunch of containers of more dilute. So it's cheaper that way as well. So what we do is we have to be able to kind of weaken these concentrated, they call them stock solutions. We have to add water to them to make them less concentrated. All right. So what we do here is we kind of rearrange this equation, and we say that moles of solute equals the molarity times liters. And then we set that equal to what we want to get it to. So this is what our formula ends up looking like in the end. Because the moles of the solute isn't going to change. You're just diluting them down. You're just changing the concentration. So here we've got a stock solution. We've got calcium chloride stock solution. We want to make 0.5 milliliters or 0.5 liters of it. And we want to have it this week. Okay. So our formula, and I'm guessing, Carly, if you look to your left there, you might even see where I've got one sitting there. Do you see where I've got that Post-it note on the hood?
Yes, you see it. I can't tell what it says.
Yeah, that's probably one of my calculations from doing something for AP, would be my guess. Yep. So that's where that's me trying to do one of these calculations to weaken some stock solution down. So this is a real common one that I run into here. So my M1 V1 equals M2 V2. So we want to get to this situation. We know that we need to get to 0.3 molar on this side times 0.5 liters on this side. We know that our stock solution is starting out at 2. We need to know what volume of that we need to put in our flask to make this stuff. Divided by 2 is 0.075. So V1 is going to equal 0.075 liters, which is 75 milliliters. So I would take 75 milliliters of this guy. I would put that into my volumetric flask. Okay, and then I would add water up to that etched line. And then I would have it taken care of. And you guys are going to have to do that. That's part of your lab that's going to be coming up.
Okay, so all you did at the end was?
I multiplied these two things together and then divided by 2 to get this value.
Okay, and then it's equals 70. Where do you get the 75 milliliters?
This is the answer.
It's milliliters?
Yeah.
Oh, okay.
Because I don't have, like, my equipment measures out in milliliters. And so.
Oh, okay. I see.
So I would grab a graduated cylinder back there and I'd measure out 75 milliliters.
Okay. I got that. Thank you.
All right. So solution concentration can change with temperature. Sometimes it'll expand or contract. And so because of that, your molarity is going to change because your volume is going to change. Does that make sense? So certain things in industry in particular take that into account, like railroad shipping, these railroad train cars and your trucks that are running with diesel, big tanks of, whatever that these trucks, have in them. They don't end up using a lot of times in industry molarity because of the temperature issues. Because a lot of times these plants are outside and the weather goes from like stupid hot in Wisconsin, 100 degrees down to, stupid cold in the winter. And so their volumes would change, which means that their concentrations would, and then their products wouldn't be consistently the same. And so they go by something called molality because the mass isn't going to change. The moles of the solute, the mass, those things are not changing. And so that's why they would use molality. This is with a little m as opposed to molarity, which is with a big M. We do not use molality in AP Chem, though. But I'd like to introduce it here because you might see it in college. You might see it later on in other things. So I want you to be exposed to it, but just realize that what we really care about in AP Chem is molarity. So this is going to be moles of solute divided by kilograms of solvent. And that's where this gets tricky, because this is the case where we don't add everything together. We're not using the solution down here. We're just looking at the solvent itself. All right, so we've got 4.5 grams of NaCl. and we've got 100 grams of water. So again, moles of solute. So moles solute divided by kilograms, and that's going to be another kicker right there, of solvent. So we need to identify what this is. Is this a solute or is this a solvent?
How do you do that? Like the way the question is phrased.
Well, which one would get dissolved in the other? Right, this is going to get dissolved in the water. So that makes the NaCl the solute, which means that we need to convert these grams into what? Moles. So we're going to take 4.5 and we're going to divide that by 58.5, and that's going to get us into moles. So that ends up being 0.0769. And I'm going to divide that by kilograms of solvent. This is in grams right now. I need to convert it into kilograms. So what do I do? I'm going to kick the decimal point one way or the other. Which way is it going to go? Which is bigger, a kilogram or a gram? Kilogram. So I'm going to kick the decimal point this way. So it's going to be 0.100 equals. So that ends up being 0.769, and that's going to be a little m. And you got to be careful with your big M's and your little m's. Like, you've got to make them distinguishable. Make sense? All right. So then the last one is mole fraction. This is going to be the moles of the solute and the solvent divided by the total mole amounts. Sometimes they use X's or little n's. It doesn't really matter. It's not a big deal. All right. So first of all, we've got our hydrochloric acid here, and we've got 36.5% hydrochloric and 62.5% water. So we're going to calculate the mole fraction of the solvent and the solute, okay? Assume that you have a 100-gram sample. If you have a 100-gram sample, that means that you've got 36.5 grams of this guy and 62.5 grams of this guy. So step one, we are going to turn these guys into moles. So 36.5 divided by 36.5. It's going to give me moles of that. And this guy divided by 18 will give me moles of that. So 1 mole of HCl. And I have, that one I can't do in my head. 3.47 moles of water. Good?
Yep.
All right, now we're going to figure out the fraction. So this is just, again, part over the whole without multiplying by 100. So this is a part, this is a part. How do I get my whole?
Oh, you
Got part, yeah, I add them together. So I'm going to add 1 and I'm going to add 3.47 together, which is 4.47. And then I just go back and divide. So this ends up being 0.224. And this guy, and there's no units on this, ends up being 0.776. These things should add up to be what? to be 1. They should add to be 1. All your parts, all your mole fractions, all the fractions should end up being add up to be 1. I think that's it for today. So I gave you your homework already. Your homework is 4-1. I'm going to be grading that. I'm going to collect it and grade it on accuracy. So make sure that you're good with that. If you've got questions on it, if you want to come up and check it before you turn it in and make sure that it's good, I'll be happy to kind of give it a pre-check for you and show you the ones that are wrong. I'd like that turned in by the time you start the lab on Tuesday. Make sure you bring your goggles in on Tuesday. Okay? For those of you at home, make sure you bring your goggles in on Monday. You're going to need them. So the rest of the time, you can either work on test corrections, finishing your tests, or you can work on your homework.